Lab 5, Magnetic Braking with Faraday. So first I'm going to do an intro, then I'm going to go into the fundamental principles. I'm going to explain the experiment, which includes the actual procedure, the initial conditions, the assumptions, and the system and surroundings. Then I'm going to explain the results, the glow slip code, and then the follow-up questions. So the purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, to model the magnet/tube interaction computationally using glow script, and then to compare my computational predictions with my observed data. And so my observed data, so the experimental time was 1.18 seconds, and then my computational time was 1.656 seconds. Some of the fundamental principles that we see throughout this lab includes Faraday's law, which is also inclusive of magnetic flux, Newton's second law of motion, and Newton's third law of motion. This is the procedure for the experiment. So first I had to mark the north pole of the bar magnet. I had to use the magnetometer app to determine which end was actually the north. And then I held the tube vertically and positioned the magnet just above the opening. I used my smartphone to record all of this, and then finally I dropped the magnet from the top and let it go all the way through to the bottom. And then I went through my video data, and I looked at the time codes of when I first dropped the magnet to when it finally came out, and then I did this 5 times, and then I added up those results to get an average time that it took for the magnet to fall through the tube. In this, the systems were the magnet in the roll of the aluminum foil, and the surroundings was everything else. Some of the assumptions held in this experiment is that the bar magnet acts as a magnetic dipole, the system is isolated and no other magnetic fields could interfere, and the magnetometer app correctly defines the north pole. Some of the initial conditions included that the length of the foil was 0.3 meters, the width was 0.006 meters, the inner radius was 0.019 meters, the mass was 0.019 kilograms, and the magnetic dipole moment that I calculated in lab 3 was 2.99. Some of the errors that could have occurred in this lab include that measurements are slightly inaccurate, time steps from a phone may have been misleading, and then the other magnetic fields are actually present and disrupt the lab. So these are the results of my experiment, and something to note is that the coloring of the tube indicates the magnitude of current flowing through each ring. So the blue is the clockwise rotation of the current, the red is the counterclockwise rotation of the current, and the blue is on top of the red. Lenz's law says that the magnetic field from the induced current opposes the change in flux, which is what we observed in this lab. As mentioned in lecture, flipping the bar magnet will not change the results of this experiment. My computational result of 1.656 seconds versus my experimental result of 1.18 seconds is only a 0.476 second difference, which is really close. And then the resulting graph, which is off to the right, tells us that multiple forces are acting on the magnet, specifically the gravity and magnetic force. So the first part of the glow script code is to create the geometry of the tube. The next part is to create the bar magnet. After that, we use a function to calculate the magnetic field of the bar magnet. Then we use another function to calculate the magnetic flux. Then on this next part, we have the simulation loop. Then we have the function to calculate the gravitational force in the magnet. Then we calculate the current in the ring. We compute the typical B field in the ring. And then we calculate the net force on the magnet. And finally, we update the magnet's velocity and position. Questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity of the conductor were reduced as close as possible to 0, then the current would be extremely high. This would cause the magnet to fall even slower within the tube. What if holes or slots were cut into the tube? How would this affect the ring current in your model? If there were holes or slots in the tube, there would be less current in the rings of the tube. This will cause there to be fewer opposing forces within the tube, which then causes the magnet to fall faster within the tube.